Welcome back. Let's continue with the ninth chapter, Work, Energy and Power. And today we'll be studying about energy, the various forms, law of conservation of energy, and the power. Is defined as the capacity to do work. There are various forms of energies like mechanical energy, electrical energy, kinetic, nuclear, solar, sound, chemical, etc. But let us study mechanical energy. Mechanical energy is the energy possessed by a body by virtue of which it performs some mechanical work. It is of two types, kinetic energy and potential energy. Kinetic energy is the energy possessed by a body due to its virtue of motion. It is the energy possessed by a moving body and it is equal to the work done by the body before it comes to rest. So let us consider a body of mass m which has an initial velocity of v and the final velocity as 0. Now as the force is being applied, let the retardation be minus a and the displacement is s. So the kinetic energy is equal to force into displacement, which is ma into s. Using the equation of motion, we find out the value of displacement as v square upon 2a. Substituting this value in equation 1, we get the kinetic energy of a moving body as half mv square. So the kinetic energy is directly proportional to the mass and to the square of the velocity. Energy theorem. The work energy theorem states that the total work done on the body is equal to the change in its kinetic energy. So let us consider a body of mass m moving with the initial velocity v1 and after a displacement of s, its velocity becomes v2 under the effect of a force F. So using the equation v square is equal to u square plus 2as, we get the acceleration as v2 square minus v1 square upon 2s. Here the value of force is ma, so substituting the value of a, we get the value of force as m into v2 square minus v1 square upon 2s. Now the work done by the external force is F dot S. Substituting the value of force, we get W as Fs cos 0. As force and displacement are in the same direction, therefore theta here is 0 and the work done comes out as half m v2 square minus v1 square, which is equal to the difference in the kinetic energy. Now, we can also give a relation between kinetic energy and momentum. The kinetic energy of a body moving with the velocity v is half mv square. The momentum is m into v. Now, putting the value of v as p upon m, we get p square is equal to 2mk or k is equal to p square upon 2m. Energy. It is the energy possessed by a body by virtue of its position or state or configuration. It can be gravitational potential energy, elastic potential energy, and electrostatic potential energy. If we have a system of charges, then the work done against their mutual attraction is stored in the form of potential energy, which is known as the electrostatic potential energy. The gravitational potential energy, as you've already studied, is the energy possessed by a body by virtue of its position and its value is mgh. The elastic potential energy is the energy possessed by a body by virtue of its expansion or compression against elastic force. Now let us calculate the elastic potential energy. As you see in the diagram, there is a spring of length L. Let the spring constant of the given spring be K and let the final length to which I increase it be X naught. So the elastic potential energy of the spring will be equal to the work done by the spring in regaining its original length. Now, when the force F is applied and the spring is displayed from x equal to 0 to x equal to x naught, then an elastic restoring force is set up in the spring, which is directly proportional to the displacement. So this force is equal to minus kx, as shown in the second diagram. If we give it a small extension of x, then the work done is equal to minus f dx cos theta. The negative sign indicates here that the work is done against the restoring force. Now the total work done by the spring in gaining its original length will be obtained by integrating it from x naught to 0. So the total work done will be equal to half kx square, which is stored in the form of potential energy, and therefore the potential energy of the spring is half kx square. Of conservation of energy states that energy can neither be created nor be destroyed. It can only be converted from one form to another. That is, the total amount of energy of the universe always remains constant. Let us take the first example of a free fall of a body under gravity and prove the law of conservation of energy. Here we've considered a body of mass m at point A, which is at a height h above the ground and is allowed to fall freely under gravity. At point A, the body is at rest, so its kinetic energy is 0 and it possesses only potential energy. Therefore, the total energy at A is mgh. At the point B, the object has fallen a vertical distance of x with a velocity v. Then v square is equal to u square plus 2gh. Here the h is x, so the velocity comes out as 2gx. Now the kinetic energy at this is half mv1 square, which comes out as mgx, and the potential energy is mgh minus x. The vertical distance from the ground of B is h minus x. The total energy at B comes out as mgh. Now, if we consider the position at the ground, that is at point C, then here the potential energy is 0 because the height is going to be 0. The kinetic energy by solving comes out as mgh. So again, the total energy is mgh at the points A, B and C. So from here we see that the total mechanical energy is always remaining constant wherever the point is along the path from A to C. This can be represented graphically by taking energy on the y-axis and the height above the ground on the x-axis. Now if you see the diagram, the small dashes is indicating the kinetic energy, while the increasing graph is representing potential energies. At h by 2, both the kinetic and potential energies are equal, and the total energy at each point comes out as mgh and is conserved. Defined as the rate of doing work. The average power can be calculated by the total work done divided by the total time taken. The average power evaluated for a very short duration of time is known as instantaneous power, and it is equal to dW by dt. Substituting the value of F as F dot S, we get instantaneous power as F dot ds by dt. ds by dt is the velocity, so the power is F dot v. If F and V are parallel, then power is maximum, which is F into V, and if they are antiparallel, theta is 180 degrees and the power comes out to be negative. The SI unit of power is watt. 1 watt is defined as the power when 1 joule of work is done in 1 second. The other unit of power is horsepower. 1 horsepower is 746 watts. The dimensions of power are ml square T minus 3.